So let's use the free computer algebra system GeoGebra to graph this function. Notice that here the time axis is the x-axis and y is a function of x. And let's zoom in and let's graph the points 0, 1.5, and 1, 6.0. And let's connect these points with a line. Now if we look at the equation for this line and we rewrite this equation in the slope-intercept form, we will see that the slope is positive 4.5. That is, on average, during the time interval from 0 to 1 seconds, the position of the object, or position of the particle, is changing at a rate of 4.5 meters per second in the positive direction. Okay, so once again, let's consider the position of a particle as a function of time given by some polynomial. Now at any specific time, t sub naught, the particle has a specific position and is moving with a specific velocity. Now notice that we cannot use the average velocity formula to determine its velocity at a specific time, because then we have the indeterminate form, 0 divided by 0. And so the way that we approach this problem is to choose a very small time interval, delta t, so that at the later time, t sub naught plus delta t, the particle has a different position, but notice that as the time interval delta t becomes increasingly small, the second point is increasingly closer to the initial point. So let's look at, first at the average velocity between these two points. We have that the position at the time t sub naught plus delta t minus the position at the time t sub naught divided by the total time interval t sub naught plus delta t minus t sub naught, which is simply delta t, is the average velocity between these 2 points. Now if we take the limit as delta t approaches 0, then we have what is called the instantaneous velocity of the point, or rather of the particle at the point t sub naught. And this limit we call the derivative of x with respect to t, and in this case we're evaluating this derivative at the time t equals t sub naught. Now notice that the instantaneous velocity of a particle at a specific time, t sub naught, has a geometric interpretation. It is the slope of the line that is tangent to the position function at the time t sub naught. And so the instantaneous velocity of a particle is the limiting value of its average velocity as the time interval delta t approaches 0. That is, the instantaneous velocity is the limit as delta t approaches 0 of its displacement divided by the time interval delta t. And this is the instantaneous change in the position with respect to time. And we call this the derivative of position with respect to time. Now if the position function is given by a polynomial, then there are 4 simple rules that we can use to determine the derivative of any polynomial. The first rule is called the constant rule. The derivative with respect to t of any constant is 0. And this should make sense since a derivative is a rate of change, and the rate of change of a constant is 0. The second rule is called the power rule. The derivative with respect to t of the monomial t to the power of n is n times t to the power of n minus 1. That is, to take the derivative of a monomial to a given power, we multiply the monomial by n and then reduce its power by 1. The third rule is called the constant multiple rule. The derivative with respect to t of a constant times a function of t is the constant times the derivative of that function, and we generally denote the derivative of the function f by f prime. And finally, we have the sum difference rule. The derivative with respect to t of a sum or difference of two functions is the sum or difference of their derivatives. And again, we denote derivatives of functions with the prime symbol. So let's look at an example. The position of a particle is given by x of t is equal to 1.5 plus 9.4 times t minus 4.9 times t squared, where x is in meters and t is in seconds. Determine the particle's instantaneous velocity at the times t equals 0 seconds and t equals 1 second. Okay, so once again we have the position function x of t is 1.5 plus 9.4 times t minus 4.9 times t squared. The instantaneous velocity at any given time t is the derivative of the position with respect to time, and we can also denote this as x prime of t, and this is the derivative with respect to t of the polynomial 1.5 plus 9.4 times t minus 4.9 times t squared. Now we can choose to group any two terms of the polynomial, and we can now apply the sum difference rule. And so we have the derivative with respect to t of the function 1.5 plus 9.4 times t minus the derivative with respect to t of the constant multiple 4.9 times t squared. Applying the sum difference rule a second time, we have the derivative with respect to t of the constant 1.5 plus the derivative with respect to t of the constant multiple 9.4 times t minus the derivative with respect to t of the constant multiple 4.9 times t squared. Now the derivative of a constant is 0. The derivative of the constant multiple 9.4 times t is the constant 9.4 times the derivative with respect to t of the monomial t to the power of 1. The derivative of the constant multiple 4.9 times t squared is the constant 4.9 times the derivative with respect to t of the monomial t squared. So we have 9.4 times the derivative of the monomial t to the power of 1, which is 1 times t to the power of 0, or simply 1, minus 4.9 times the derivative of t squared, which is 2 times t to the power of 1, or simply 2t. And so this is 9.4 minus 9.8 times t. So notice that just as the position is a function of t, so too is the velocity, the instantaneous velocity, a function of t. And so the instantaneous velocity of the particle at the time t equals 0 is 9.4 meters per second. And the instantaneous velocity of the particle at the time t equals 1 second is 9.4 minus 9.8 meters per second, or negative 0.4 meters per second. Now recall that the velocity at a given time is the slope of the line that is tangent to the position function at that time. And so we can find the equation for the line that is tangent to the position function at those given times. So for the time t equals 0, using the slope-intercept form of the line, we have x minus x of 0 is the slope, which is the velocity at the time t equals 0, of t minus t sub naught. So we have x minus 1.5 is 9.4 times t minus 0, or simply t. so that the equation for the line tangent to the position function at the time t equals 0 is 1.5 plus 9.4 times t. Again, notice that the slope of this line is the velocity at that time. So at the time t equals 1, we have x minus x of 1 is the velocity at the time t equals 1 times t, the quantity t minus t sub 1, where t sub 1 is the time 1 second. So we have x minus 6.0 is equal to negative 0.4 times t minus 1, which is the equation x equals 6.0 minus 0.4 times t plus 0.4, which is 6.4 minus 0.4 times t. Again, notice that the slope of this line is the velocity, the instantaneous velocity at the time t equals 1. So let's once again graph the position function using GeoGebra. Now we can use the computer algebra system to evaluate a derivative symbolically. So let's check our velocity function. So we have the position function, 1.5 plus 9.4 times x minus 4.9 times x squared. And we'll take the derivative. And if we convert the fractions to decimals, we will have the same velocity that we have already calculated. So let's once again plot the points A and B, where A is the point 0, 1.5, and B is the point 1, 6.0. Now this time we'll also plot the lines that are tangent to this curve at the point A and at the point B. So at the point A, we have the line 1.5 plus 9.4 times t, times x. Notice that this line is indeed tangent to the curve at the point A. And so at the point B, we have 6.4 minus 0.4 times x. And once again, notice that this line is indeed tangent to the curve at the point B. Now we can also use the velocity function to determine the inflection points for the position function. And these are the points where the particle changes direction, and the inflection points occur where the velocity function is equal to 0. And so for our velocity function, which is 9.4 minus 9.8 times t, we will set this to 0 and solve for the time t. So we have 9.8 times t is equal to 9.4, so that t is 9.4 divided by 9.8, which to two significant figures is 0.96. So at this time, the velocity is 0, which means that the slope of the line tangent to the position function at this time is 0. That is a horizontal line. And so we have the horizontal line x minus x of 9.4 over 9.8 is equal to 0, which is the horizontal line in the xt coordinate system. X equal to the value of the function, position function at the time, 9.4 divided by 9.8. So once again, let's plot our position function in GeoGebra. This time we'll plot the inflection point, which we'll call I. And this is the point that occurs at the time 9.4 divided by 9.8. And at the position, f of 9.4 divided by 9.8. And the line that is tangent to the curve at this point is the horizontal line of constant value f of 9.4 divided by 9.8. And notice that this is indeed a line of zero slope. The velocity at this point is 0, and that this is the point at which the direction of the particle changes. So we can tell quite a lot from a position versus time graph. For any given point on the position versus time graph, we can visualize the velocity as the directed line segment that has a slope equal to the slope of the line tangent to the curve at that point, and a length equal to the magnitude of the velocity. Here we have a positive velocity, and here we have a negative velocity. Now notice that this graph has two inflection points, which we'll call A and B. So during the time interval from 0 to the time t sub A, the velocity is positive but is decreasing. And we know that the velocity is decreasing since we go from a positive slope to a zero slope. And at the time t sub A, the velocity is 0. During the time interval from t sub A to t sub B, the velocity is negative but is increasing. And we know that the velocity is increasing since we go from a negative slope to a zero slope. And at the time t sub B, the velocity is once again 0. Now recall that this is one-dimensional motion, and we can identify three important points on the x-axis. We have the initial position, the position at the inflection point B, and the position at the inflection point A. So for this particle, we start at the point x sub naught. It moves in the positive direction, momentarily comes to a stop at the inflection point x sub A, changes direction, momentarily comes to a stop at the inflection point x sub B, and then changes direction, once again moving in the positive direction. Now the speed of a particle is the magnitude of its velocity, and for motion in one dimension, this is the absolute value of the velocity. And so the instantaneous speed of a particle is the absolute value of its instantaneous velocity, and the average speed of a particle is the absolute value of its average velocity. Notice that this is the same as the distance that the particle travels divided by the time required to traverse that distance.